Okay. Last lesson, we looked at derivatives. Okay. What's the gist of what a derivative does?
Finds the line that is tangent to any one point on a function.
Pretty much. What does it find about the tangent? The slope. Okay. All right. And we saw what we had is we had kind of a formal definition, and we used limits in order to formally define what a derivative is, and then we found, oh, here's a much more straightforward, simple, quick and easy way of doing it, right? We get kind of the same thing with integrals next, except we have one entire lesson of just the lengthy way of doing an integral, and then we'll have a follow-up lesson, lesson 4, that is, here's the quick, easy way of doing it, which that's called the fundamental theorem of calculus. Okay? So if the derivative is finding the slope of the curve at any given point, an integral is finding the exact area under a curve. So what we mean by that is this. Let's just say, so we'll get our axes going here. X-axis, y-axis, and let's say we have some curve. No, actually, I don't want to do it like that. I want to make it one steady slope. That'll be easier to do it. Let's say we have some curve that does this. Okay? And we want to find, say, from here to here, this exact area. That's what we mean by the area under a curve. Okay? We're talking from some particular x value to some particular x value, what the area is of the region that goes, oh, Jake, can you see where I'm drawing here?
If you don't write anything below
Okay.
the graph.
Okay, all right. Yeah, I just realized, oh, that might be blocking your side. If I'm over here, you're good though, right?
Oh,
okay, all right. So yeah, the area under, or from some x value to some x value between the curve and the x-axis. Okay? If this were all straight lines, no problem. Algebra will serve us just fine, right? But the curviness here is what starts to cause a problem. That's why we're going to need limits. So I'm going to get rid of the shading so I can introduce an idea. And just like what we saw with the derivatives, well, let's say we make it 2 points and we approximate the slope. And then we move the point closer and approximate. And then move it closer and then find what the approximation is as the distance between the 2 points becomes 0. Similar idea, we're going to call this initial x value here, we're going to call it A. And our ending x value, guess what we're going to call it? B. Yeah. Okay? And the idea is, well, what if we took this curve and let's just say we split it into 2 rectangles. And so we said, well, we have this rectangle, and then we have this rectangle. Pretend they're the same width. I didn't do a super good job getting that, but pretend they're the same width. Okay? Would we be in the ballpark of what the area is if we found the area of this rectangle and added it to the area of that rectangle? Yeah, I mean, decent, but we're overshooting it, right?
Yeah.
Okay. Well, what if instead of just the 2 rectangles, we made it 4 rectangles? So I'm going to get it a little bit closer to even here. And so I was too far to the left, so maybe about like there, and then about there, and then about there. And so we have that rectangle, this rectangle, that rectangle, that rectangle. It's closer. Does that make sense? Okay. If we split it into even more rectangles, it would be closer. If we split it into more rectangles, it would be closer. I think you can see where this is going. So what an integral does is essentially this. It takes this region and it splits it into an infinite number of rectangles.
Until it gets closer and closer to the...
Yeah, and the more rectangles you split it into, the closer you are to the exact area. So what we do is we find the area as the number of rectangles approaches infinity. We find that limit, the limit of the area as the number of rectangles approaches infinity. But this does get to some of that weird stuff with infinities again. Remember how once or twice earlier this year we talked about a line segment? And how a line segment is made up of an infinite number of points? What's the dimension of each one of those points? Or not the dimension, but like what is the width of each of those points? Has the width of 0. A line segment has a finite length that is achieved by putting together an infinite number of things that have length 0, or at least, yeah, okay. That kind of idea, it's like it doesn't quite make sense, but it kind of does make sense. Same thing here, we're going to end up getting a finite area that is made up of an infinite number of infinitely thin rectangles. But you find the area of an infinite number of infinitely thin rectangles, and you get answers like 1/3. Stuff like that. Okay? Yeah, there are certain things you just kind of have to take at face value a little bit, and yeah. Let's add a couple pieces. And if we said that this function is just f of x, right? Okay. And our a values go from a to b. Okay. Or sorry, our x values go from a to b. And we're going to say that what we are adding here is some distance that we'll call delta x. Delta x. So what we're going to be making is, as we add more rectangles, delta x gets smaller and smaller and smaller. Delta x is the width of the rectangle. We make it smaller and smaller and smaller as we increase the number of rectangles. Okay. So then this is a delta x. Another delta x. This is a delta x. Okay. And for this one, we only have 4 delta x's. Okay, good so far? So if this, our first x value here is, we're just calling it a, right? What would be the x value right here? Right there. It would be a plus delta x. That make sense?
Yeah.
And then if we take that x value here, so I guess I'll write here, this is a plus delta x. Okay. That is that x value right there. Good? So that's an x value. If we plug that x value into our function, what do we get? But the height of the function. Let's just say our function is 3x plus 2. I say, what's your y value when x is 4? What do? You take that 4, you plug it into your function. Your function...
but we need the function equation.
Yeah, we don't know what this is some generic function. We don't know what the equation is. Okay, so the general idea is, here's an x value. Plug your x value in for x in your function, and what does it spit out? The y value on this graph. Okay, so with that in mind, does it make sense that the height of this rectangle, okay, so we talked about the x value, that the height of this rectangle is f of a plus delta x. Whatever that y value is, that is the height of the rectangle. That idea good? So what would be the area of this first rectangle? Area of a rectangle, width times height. What's the width of that rectangle? So area of a rectangle. I did hear your answer. I'm going to come back to it in just a second. Area equals width times height, right? Okay. Well, the a plus delta x is the ending x value. It's the x location of the end of the rectangle.
Oh, yes.
So what the actual width of the rectangle is delta x. How wide is that rectangle? Delta x. Good? Okay. So we have a delta x is the width of the rectangle. What's the height of that rectangle?
Is it f of x, f of a plus delta x?
F of a plus delta x. It's that value there. Times f of a plus delta x. Now, if we do these, we get the area of that first rectangle, right? So maybe I'll call it a sub 1. What would be a sub 2, the area of our second rectangle? What's the width? It's still delta x, right? What's the height now, though? It's an f of a plus 2 delta x. Because we added 2 of those delta x's to get to that new x value. That makes sense? By the way, just one little side note as a heads up, if you take calculus in college, some textbooks base the height of these rectangles based on the ending x value, right? In which case we took the ending x value and that's where we drew the height of our rectangle. Some textbooks use the beginning x value to draw the rectangles, in which case if we did that, our rectangles would be too short each time, and we would be less than this area. Some go with the midpoint between each two. And so it's like slightly different notation sometimes. It's the same idea. More commonly than not, I see the definition of things being based on the final.
Is the formula come out to be
The formula ends up being the same. Yep. And the approach ends up being the same. Yep. And you would get the same answers. Yeah. All right. This idea makes sense? So what we need now is a way to start representing things where it works. We can have a simplified notation to represent what ends up being an infinite number of rectangles. Okay? So I think here's what I'll do. We have the idea in place. I'm going to write the formula, and then we'll start to talk about it. Okay? As well as some new symbols. This symbol here, and that's not a good start to it, is an integral symbol. Okay? And we designate, assuming we're finding the integral as we go from one particular x value to another particular x value, the starting x value goes there, and the ending x value goes there. So this would be read the integral from a to b. The integral from a to b. Of f of x dx. F of x, that's just whatever function we're finding the integral of. Okay? The dx means we have a starting x value and ending x value, and we're finding the area between the curve and the x-axis.
Can you say how you say that?
Yes, this would be the integral from a to b of f of x dx. Okay? And I don't think it really comes up until you're dealing with calculus 2 that you start to deal with sometimes where it's easier to deal with dy, where you actually start finding the area between the curve and the y-axis as you go from one y value to a different y value, and it just changes your perspective. And sometimes you can have a problem that's nasty to solve one way, and you just redefine it to be a different way of looking at it, and it can simplify things. But we only deal with dx. Okay? And here's the formal definition of an integral in this case. So we're finding the limit as n approaches infinity. Guess what n is going to refer to? Basically how many rectangles we're dealing with, okay? of the sum from I equals 1 to n of, I guess, the arrangement. Here we're dealing with the width of the rectangle times the height of the rectangle, right? I'm just going to flip-flop those and go height times width, just because it'll keep me consistent with the textbook here. F of x sub I delta x. I'll explain the x sub I part here in just a moment. Okay? Delta x already makes sense, right? The width of the rectangle. F of x should make sense, the height of the rectangle. The x sub I is to make it work with this sigma notation. What this is saying, because sigma notation is sum of, right? It's saying when I equals 1, you're dealing with your first x value plugged in. Plus, I equals 2, because you're right, you go up by integers. Your second x value plugged into your function. Plus, your third x value plugged into the function. Plus, and each time you do that, you're multiplying by the width. So this is basically saying the height of the first rectangle times the width, plus the height of the second rectangle times its width, plus the height of the third rectangle times its width, plus the height of the fourth rectangle times its width. Do that n times and find what the limit of this expression is as n approaches infinity.
Is I not an imaginary number then?
No. Good question. I is commonly used in sigma notation and is commonly used in computer programming as, I think most would say it stands for index. It is our index of items. As our first item, our second item, our third item, our fourth item. Yeah, so good question, not I as in the square root of -1. Okay, so there are a couple things that we need to define here. Delta x, we kind of defined already. Delta x, and we can add this to our definition basically, where delta x equals your ending x value minus your initial x value, b minus a, over n. Was take how wide your area is, divided by the number of rectangles you're making out of it, and you get the width of each rectangle. Okay. So in this case, if let's just say A were 1 and B were 13, 1 to 13, what's that width? If this went from 1 to 13, the width is 12. And if I cut it into 4 rectangles, how wide is each rectangle? 3. Right? 12 divided by the number of rectangles, 4. So that's what this is dealing with. The width of each rectangle is take the width of the total region divided by the number of rectangles. Is that good? Okay. And we need 1 or 2 more pieces here. X sub I and x sub I equals, because x sub I is the x value that we're plugging in to our function, right? Now we already looked at what the first one is here. The first one here was a plus 1 delta x. Our second x value that we're plugging in would be a plus 2 delta x. Okay? So we can already see we're going to start with a, and we're going to add to that. Any thoughts? If I is 1 for our first, what was that? Almost. N is representing infinity here. So n is approaching infinity. Okay. Here, I is 1 for our first point. I is 2 for our second point. So if we're adding 1 delta x to get to our first point, our first x value. Then we're adding 2 delta x's to get our second x value. We're adding 3 delta x's to get our third x value. Does that make
I
sense? I can
factorial.
use I delta x.
No, I did not follow.
Okay. I is representing 1, 2, 3, 4, 5, etc. Okay?
Okay.
For our different x values. What is our first x value? X sub 1 would be our first x value. How do you find x sub 1? Well, let's see, our first x value. We take a and we add 1 delta x. X sub 1 is a plus 1 delta x. How do we find our second x value? Well, we start at a and we add 2 delta x's. Our second x value, we add 2 delta x's to a. So our second x value, we do a plus 2 delta x.
Okay.
And it's following the pattern of I is just going 1, and then 2, and then 3, and then 4.
Okay. Yeah.
You feel better about that?
Yeah.
Okay.
But it ends up being the same as A. Right?
Yes. And there's well, you'll see.
Except
There's one really important piece of the puzzle that we haven't added yet that I think will make more sense to add once we start to do a problem, and we'll see the kind of issue that we run into where we need to add that final piece of the puzzle to fix it.
Okay.
Okay? All right. Let's do one. Okay, so here's what we want to find. Here's what we want to find. We'll start out. We want to start out with like about the easiest example we can, or maybe something one step. All right, we'll start with
these.
All right.
Easier.
Okay, we'll start out with here then. Can I erase this? I'm gonna need space. All right. You have this down easy to see on your notes. Okay. All right. So here's what we want to find. We want to find. I don't need it quite that big. We want to find the integral from 0 to 1 of x squared dx.
So I
So,
don't think it looks like pictures.
correct.
So there's only one step.
No, this is our integral notation. We can do it from whatever to whatever.
Oh.
Yeah. The I was showing up with the sigma notation.
Right.
Yeah, that summation thing, which we don't have here yet. Okay. So visually speaking, graphically speaking, what we're dealing with is a parabola, right? Centered at the origin. And we'll just say that we're going out to -1 there and +1 here. And I would keep going a little more like, we'll say like that. That we want to find this exact area between the parabola and the x-axis going from 0 to 1.
How do we do this problem?
Just because of what the function is, x squared.
Oh, okay, so are we multiplying the x squared by dx?
No. This is not a multiplication
Okay.
thing. This is to identify, this is to let us know that what we're doing is we're scanning along the x-axis, that 0 to 1 are x values. And we're finding the distance between the curve and the x-axis. That's what the dx is. It's informative. It doesn't actually like multiply or alter other than provide information about what we're dealing with.
That is useful.
Okay, yeah. Okay, good so far? All right, so then what we're doing, what this equals then, is the limit as n approaches infinity of the sum from I equals 1 to n of x sub I squared delta x.
Do we have to come up with that? Or was
Yes.
that part of the problem?
This is the formula that you'll need to memorize.
Yeah.
And what I did is I took what the function is. My function is x squared. And I just replaced the x, or if there were multiple x's, I'd replace all of them with x sub I.
Okay.
That should be a good idea now, that f of x sub I, if f of x equals x cubed minus 3x plus 1, then f of x of I is x of I cubed minus 3 times x of I plus 1, right? So I rewrote the formula exactly, except instead of an f of x of I just rewrote my actual function with an x of I. Now to play it safe, it might be a good idea for you to write here first f of x of I. And then in your next step, swap in your function. That make sense?
Yeah.
Okay. Now kind of off to the side here, we want to find this. I'm going to say first, find delta x. You have a formula for that.
Do?
Yes. It is b minus a over n.
It's the same thing as x of I.
No, it's going to be helpful to find x of I. We have a separate formula for x of I that you should have in your notes.
Oh, this is the video.
Yes.
Oh.
Yep.
Sorry, I have, they're right next to each other. So.
Yeah, gotcha. So what's my b value?
1.
1. What's my a value?
0.
0 divided by n. So delta x is, okay, that's all right. 1 over n. Okay, hang on to that. You're going to need that. Good so far?
Yes.
Okay.
Yes.
Now we need to find what x sub I is. And you had a separate little formula for that.
Yeah.
It was a plus I delta x. Now there are two things we can, I guess I would say second, find x sub I. We can plug in what a is. What's a?
0.
0. We can plug in what delta x is. 1 over n. So when I simplify, I just get either, you could write it either way as I times 1 over n, or just I over n. Okay? All right. Okay. So here's what this is saying. The width of each rectangle is 1 over n. So because we took an area that is 1 unit wide, and we're cutting it into n rectangles. So the width of each rectangle is 1 over n. This is saying the x value that we get to is I over n, where I goes 1, 2, 3, 4. So if the width of each rectangle is 1 over n, what is the right-hand side of your first rectangle? 1 over n, because you went 1 over n to the right. Then you go 1 over n to the right again, and what's your x value now? 2 over n. Your second x value is 2 over n. You do that jump to the right again, and your third rectangle's x value is 3 over n. Does that make sense? Okay, now we have the pieces to plug back in here. Let's see what happens. So this equals the limit as n approaches infinity of the sum from I equals 1 to n of, and I plug in what x sub I is now. What is x sub I?
I over n.
I over n. So we're doing an I over n squared times what's delta x?
1 over
1 over n. Yep, exactly. So again, what we're dealing with here is, here's the x value, I over n. The x value beats a rectangle. And then when you plug that into the function, what's our function here? Square the x value. That gives you your y value. Take the x value, square it, this is the y value. This is the height of the rectangle. We multiply it by the width of the rectangle. And that's our first one. Plus the second one, which is 2 over n squared, that's the height of our second rectangle, times the width of the second rectangle, plus, now we're at I equals 3. 3 over n is the height of our third, 3 over n squared is the height of our third rectangle times the width of our third rectangle. Good? Okay, so let's see what starts to happen, and here's very soon, we're going to add this one other piece to the puzzle.
So we just have to start putting things in for I.
Not per se. I'm going to simplify this just a little bit, because we have kind of two things going on. We have sigma, right? And we have a limit.
Yeah.
Yeah. And what we want to do is we want to get rid of the sigma. Okay? And there are some formulas that we're going to use. And this is that last piece of the puzzle. I'm going to come, maybe, can you see okay right here? Okay, this is kind of a little to the side. We had a formula earlier for 1 plus 2 plus 3 plus ... plus I. We used n before, but I'm going to say plus I. That formula is this. No, actually, I am going to use n.
What's the fourth term? Let's see, that's 4.
Yeah, 4, 5, 6, etc. Yep, plus n. This was n times n plus 1 over 2. This is just a formula that people have figured out over time and proven. Okay? There's a separate formula for 1 squared plus 2 squared plus 3 squared, those are squares, plus ... plus n squared. There's a separate formula for that. And it ends up being n, now I can just write n there, n times n plus 1 times 2n plus 1 over 6. In other words, 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared is equal to 8 times 8 plus 1 times 2 times 8 plus 1 over 6. Right? We good with what's going on here? Okay, so check this out. We have sigma notation. I'm going to just kind of, in a sense, multiply this out. So when I square the I get I squared, right? Good? And then when I square the n's, well, actually I square that n and then I multiply it by another n. So that's an n cubed. Yes? Okay, I'm going to rewrite this. I want my I by itself. It's just easier to view. So I'm going to represent this actually like this. Oops, I didn't write the sum. Times the sum from I equals 1 to n of I squared times 1 over n cubed. I squared times a 1 over n cubed. Okay. Now if I started to write this out, if I started to write just this sigma part out, okay, I started to write just this out, I would get, first I is 1, I would get 1 squared times 1 over n cubed, right? Plus 2 squared times 1 over n cubed, plus 3 squared times 1 over n cubed, plus 4 squared times 1 over n cubed, and I'll keep that going. 1 squared plus 2 squared plus 3 squared plus 4 squared plus ... I have a formula for that. Because how high are we going in terms of I? I is going all the way up to n squared because I'm squaring I. So what I have is 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot 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 plus n squared. What is 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared? That. Okay, so check this out.
Multiply that by 1.
So check this out. Yeah, I can take the sum of I squared, the sum plus plus plus, the sum of I squared, and I can replace that with n times n plus 1 times 2n plus 1 over 6. And everything else just drops down. So I'm dealing with the limit as n approaches infinity of this times 1 over n cubed. Now look at where this leaves us. We no longer have segment that we're dealing with. All we're left with is a limit in terms of n and an expression with a bunch of n's in it. At this point, we're just finding a limit, and you know how to do that already. So let's see what we get. Stick a blue. So we need to multiply this out. Limit as n approaches infinity of, let's see what our top is. I'm going to leave the n, and I'm going to do the second and third chunks there first. That's just easier for me to do mentally. So n times 2n, that gives us a 2n, it will be squared, but then when I multiply by the n, it becomes a cubed, right? Plus n plus 2n, so it becomes a plus 3n squared, because plus 3n squared, plus n, well, plus 1 times 1, so plus 1n, so plus n over 6 n cubed. Is that an acceptable amount of skipping work for right now?
Oh, plus n because we have to do offset.
Yeah, yep. Okay, now we just have a limit. We have a 2n cubed as our leading term and a 6n cubed as our leading term. So the limit is,
1/3.
yep, 2 6, which simplifies to 1/3. And that is the area under that parabola from 0 to 1.
I'm glad we did a simple one first.
I mean, it gets slightly more involved if you're starting with something other than 0, or if your function has multiple chunks to it. That's it. The idea of what's going on doesn't change at all. You just might have a couple more things that they're going. So the idea, here's the height of the rectangle, here's the width of the rectangle. We found the width of the rectangle, the height of the rectangle. In terms of our situation, we plugged in the height and width, and then we use the sum of I squared, the formula for it, to replace the sum of I squared with what the sum of I squareds equals, and we solve the limit.
So, are you going to be using the sum of I squared? I mean,
If we have an I squared there, yes. If this were just like x plus 3,
use that.
then we would have ended up with just an I to the first, because we're not squaring x in our formula. If you have an x cubed in your formula, you need the formula for 1 cubed plus 2 cubed plus 3 cubed, etc., which I don't ask you to memorize that one. I ask you to memorize these two. If you need an x cubed or an I cubed formula, sum of I cubed formula, or a sum of I to the 4th formula, I'll give those to you.
So if it was just like plus I plus 3? What was the example?
But I think like 3i plus 1, something like that.
Or so what would we use the first?
Yeah, you use the first one, it'd be 3 times this. Then you have a plus 1. And I'll have to look at what happens with the plus one. Because technically with the sigma notation, you have that plus one showing up each time you add, right? It's a plus one,
Right.
plus da-da-da plus one, plus da-da-da plus one, plus da-da-da plus one. And how many times do we end up adding that one? N times. And so if you had like a 3x plus 1 as your original equation, then that plus 1, when you get rid of the sigma, it needs to become a plus n because you added 1 to your expression n times. If it was a plus 3, then it would need to become plus 3n because you added 3 n times.
But with limits of together.
With limits, yeah, things come out nicely. Yep. Okay, that's the long and intricate way of doing an integral. Tomorrow's lesson, we get the short, simple way. It's almost as easy as derivatives, the short and simple way. Yeah.
Okay.
Yeah, okay.